Hello everyone and welcome back to the third part in this lecture on modeling in chromatography. In this last part I'm going to give a short introduction and overview over CADET. CADET is an open source free to use modeling toolkit for mechanistic modeling of chromatography. It is developed and supplied by the Forschungszentrum Jülich. Please feel free to check out their GitHub account if you're interested. Also take note that there is a practicum, a seminar each semester where you can learn more about CADET, about the application, how it works. So if you're interested in that, please also check it out and maybe you can meet me there next semester. All right. Um, I'm gonna cut the explanation of how CADET works, especially quite short, but we want to try to implement what we learned in the last two lectures. So for the beginning, we want to start with a simple model of a breakthrough through a chromatography column of one component. And for this in CADET, we're going to try to build this experimental setup. We will have an inlet. Here our system starts. We will have a column in the middle and then an outlet at the end. For this is how the surface of the Python surface of CADET looks like. I'm using Visual Studio Code, but you can work on this in any visualizer, any editing software. All right. So at the beginning of the process, I define an inlet. This is where our system is going to start, and I'm going to set up some parameters of this inlet. Namely here the concentration of our component at 1 mole per cubic meter, which is 1 millimolar. And I'm also going to set up a flow rate at the inlet, which is going to be in cubic meters per second. So this is 1 times 10 to the power of minus 6 cubic meters per second. This is going to be our inlet definition. Then we define an outlet. This is where our system ends. And now we define a column in the middle as seen in the graphic before. And here you can maybe already see we're importing a transportation model that we want to apply, which is the lumped rate model without pores. We learned of this in the lecture before. And now we have to supply this column with some parameters. We have to define the total porosity of the column, the diameter, the length, and the actual dispersion. Those are all in meters, and this is, again, cubic meters, square meters per second, I think, all in SE units. And then we have to tell the system how these unit operations are connected, right? We have inlet, outlet, and column. And we connect the inlet to the column and the column to the outlet. And then we set up some parameters for the simulation. Here, the simulation time, 50 times 60, so 50 minutes. And then we execute this and we can watch the breakthrough. Exactly. And so here you can see the breakthrough of our one component through the column. It takes around 20 to 30 minutes to fully break through until in the outlet we have the same concentration as in the inlet. And as you can see, this is not a sharp step, but rather an S-curve, and this is due to the actual dispersion. You can also try this if we set the actual dispersion to 0 up here and try to execute this again. You see we have a much sharper increase. Not completely right, but this is due to mathematical dispersion or mathematical inaccuracies in the model. Depending on the resolution we chose, now we have the standard resolution. At a high resolution, you would have these sharp peaks. All right, let's change this back. And now we can do interesting things like maybe connecting multiple of these columns in a row. So here we define a second column that has the exact same parameters. We call it column 2. We have to make some adjustments to the connections in our system. So now the inlet connects to column 1 to column 2, and column 2 to the outlet. And then we simulate again for 50 minutes. And plot the results. And as you can see now, we can't see the breakthrough, which is quite obvious because now we have two columns in series, which means there's a larger volume that the molecules have to pass through, or the flow has to pass through. If we maybe change the time, we can see that we have a rather faster breakthrough. All right, let's come back to this first one. This one looks quite nice. Let's play around a little bit with the adsorption parameters. Let's make the actual dispersion much faster. And then you can see the S-curve is much sharper. If we obviously reduce the actual dispersion, make the value smaller, we have a sharper breakthrough. So these are all interesting things that you can already do with a few simple blocks of code. All right, this is maybe a little bit boring, so let's go to something more interesting, looking at adsorption models. Adsorption models we also talked a lot about in the screencast before, and here in CADET I've already shown you the table with all the available adsorption models. Here in CADET there are a lot of absorption models available. So we want to now look at how these adsorption models behave in reality. So we define a component system, one component, let's call it A. And for this component, we choose now a binding model. And the binding model is Langmuir. We heard of Langmuir before. And for Langmuir, we have to determine an adsorption rate and a desorption rate, because we chose this to be true, that the system is kinetic. And we also define a Qmax, a capacity of our system. Then we have to again look at some unit operations. Now we don't have a column here, but a CSTR, so a continuously stirred tank reactor. And for this, we have to define a volume of the liquid and a volume of the solid, right? So this is liquid phase, stationary phase. You can see it's around 50-50 between both. And then we again define an inlet, and this inlet component system has a concentration of 0 for our component A, and we have a flow rate of 1 to the 10 to the power of minus 3. So this is again cubic meters per second. We have an outlet defined. We have to connect all systems again, and then we simulate this. And now we can see that over time the concentration in our system is increasing. Maybe now we play around a little bit with the adsorption parameters, and setting this up, we have now this full component system with an outlet of our reactor, right? So over time, the outlet concentration is a little bit higher because molecules are accumulating. Okay, and now we want to see how this adsorption model works for breakthrough in an actual column. So we have set up here a column system. Now we have two components, components A and B. We don't have a kinetic system anymore, so it's instant equilibrium. And now we have to define absorption, desorption rates for two components, for component A and for component B. And right here we're setting up that the adsorption rate for component A is twice the adsorption rate for component B. Setting up the rest of the system, again, we choose a CSTR, all as before, and plot the breakthrough through the CSTR, and you can now see that component B comes out earlier out of our system, or component B breakthrough stronger or earlier than component A, and this is because component A obviously is binding more to our solid phase, therefore it's less available in the liquid phase for the breakthrough. Maybe you can make it even stronger. Right, so now component A is even more strongly binding to the stationary phase, and therefore is not coming out of our system as fast as component B. We can make this even stronger. Let's put it to factor 10, and then you can see that A is much more binding again. So this is how molecules behave if they bind to a stationary phase. And now we also want to do this in a column. So it's pretty much this exact same setup. We again have two components, and we choose the kinetic to be true now, and we supply a model capacity. We choose again lumbrate model without pores, put in some parameters for our column, namely the porosity, the diameter, the length, and now we also have to connect this transportation model with a binding model. And here we import the binding model we defined up here, the Langmuir model. We connect our system, and then we can simulate this. And as you can see, the breakthrough through the column looks a little bit like this. Which just means that component B is breaking through more strongly in the beginning because it's binding less strongly to our surface. However, over time, it finds an equilibrium of, however, over time, all the binding spots are occupied, which means that at some point, the concentration in the outlet is going to be the exact same concentration as in the inlet, which we defined as 1 for both parameters. Okay, but as you can see, the concentration of B at the outlet is at one point higher. And now this is due to both components competing for the same binding spot. This means that in the beginning, both A and B are binding. However, the surfaces or the adsorption, the stationary phase surface is quickly saturated. And then since component A is binding more strongly than component B, it is removing component B from the surface, which is why at some point we have a higher concentration in the outlet than we even had at the inlet, because some of the molecules that were bound are already being removed by A until all of the system is saturated at some point. Again, obviously now we can play around again a little bit with these parameters. If we make this even more stronger, the peak is going to be even more sharper, right? So in all of this region, no component A is eluting from the system, is coming out of the column. It's all just B. So this is all just molecules of B that have bound in the beginning here to the column that are now being replaced with A, and therefore A is eluting much later than B. All right, this is all nice and well. However, we also want to use these chromatography or these chromatographic models for something. Here we're setting up an experiment where we're combining a tracer that is not binding with the column with some binding columns. This is like I said in the video cast before, a dextrane pulse injection combined with a Langmuir experiment. So we have three components now, dextrane A and B, and we are setting up model parameters for these again. So we have three values now in our list. First one for the dextrane, second for the A, and third one for the B. As you can see, this dextrane cannot adsorb to the surface. The rest is quite similar. The only difference is we are now using a lumped rate model with pores and not without pores. As explained before, this adds another layer of complexity to our system. We are actually now simulating pores. So now we need parameters for the system like particle radius, particle porosity, and film diffusion. So this is the mass transfer coefficient that calculates the resistance of the molecules going into our particles. We again have an outlet, we can connect all these systems as we want to, and now we're also doing some time events. So after some times, we have an ejection. After 0 seconds, there's going to be an injection at the inlet where all our three components are going to be at 1 millimolar concentration. And after 50 seconds, the concentration in inlet is going to go down to 0. So for 50 seconds, we have an injection. And for the rest, 1150 seconds, there's going to be no more injection in the inlet. Let's see how this looks if we execute it. All right, so in the first 50 seconds, so up until around the 1 minute mark, we're adding all three components to our system. However, we can see the retention time of the components across the system differs, and this is depending on the adsorption rate. Dextrane, which we set to an adsorption rate of 0, obviously does not interact with the stationary phase, therefore washes through the column quite quickly, and the retention time is only defined by the flow rate of the convection, the actual dispersion, and the volume of the column. Component A and B, however, are interacting with the column, so they are binding to the column, and they're also desorbing from the column. And because component A is adsorbing less strongly to the column, it is desorbed earlier than component B, which gives us this separation. So if we think about this being a mixture of proteins, we already achieved quite a nice separation by doing nothing but just injecting them on the column. We can also change this to be a little bit higher even, and now we got a clean separation between our target molecules. We can do the same thing now for multiple injections. Here we're just using a feature that we are cycling this simulation 3 times, and now we get 3 times the simulation. Now to an even more realistic application, we're going to look at an example where we do a wash, load, and elute cycle with the 3 components. We are now looking at 2 proteins, protein A and protein B, and a salt. And we have the salt because we're now not using Langmuir anymore, but steric mass action, one of the 3 adsorption models I've showed you before. And this steric mass action is often used for ion exchange processes where we have a salt component, in this case our salt. So 3 components. The first component is again for the salt, and then we have component A and B, and we're now setting at absorption desorption rate. And as explained in the theoretical part, the SMA model takes into account a characteristic charge. So this is a value of how many binding sites does one molecule of this component interact with. And here our component or protein A interacts with 10 binding sites, protein B with 5 binding sites. Then we have the steric factor, and here both A and B are assigned the value 50. This means that one molecule binding to the surface also restricts 50 additional binding sites from being used by the other molecules and the salt. We then have to define a capacity of our column. This is this Q0 mentioned in the lecture. And these are internal references because the charge is going to go into the exponent of the equation, which means that the values can get really large really quick. So we're using a reference concentration to normalize some of the values. However, this is purely mathematical system of the model and doesn't impact our solution. We then define a flow rate, and now here for the transportation model, we are choosing general rate. General rate means even more complexity piled on top. We now also got a diffusion inside of the pores, and we got a diffusion on the surface. However, the diffusion on the surface we turn off by putting the values to 0. All right, we again have an inlet-outlet column system. We connect them correctly, and then we determine a cycle time. Our process is to take up 20,000 seconds. And since this is a bind, wash, elute cycle, we have to define some timely events so that the wash starts after 4,500 seconds, and then the gradient of the elution of the salt will start after 6,500 seconds. And then we're going to run a concentration gradient from 300 millimolar from 70 millimolar to 300 millimolar salt in this time frame. And here we define the initial states of our system. So at the beginning, the liquid phase is completely filled up with 180 millimolar concentration of our salt, and the column or the stationary phase is also completely saturated with our salt. All right, let's run this experiment and see how this system looks. All right, really nice. What you can now see here is the full process over 350 minutes. You can see the binding phase in the beginning up until around, well, what's that, 80 minutes. Then we have a wash phase from 80 to around 120 minutes. And then from 120 minutes onwards, we have the salt gradient where we slowly increase the salt concentration, therefore force our molecules to elute. So here, the salt ions are competing with our bound protein around the available binding spots. As you can see, since protein A is binding or is bound more strongly due to, as you can see here, the higher adsorption rate, and from the adsorption rate divided by the desorption rate, you get the K equilibrium. So this is twice as high. So it's binding more strongly. It is eluted later than the protein B. And this is how a typical, well, separation process might look. We have now a salt gradient. One could also think about doing a step elution or doing an isocratic elution where we have like one single step in between. And this is already a problem that one could look into optimizing, right? How do we optimize the separation between these two peaks? As you can see right now, they're overlapping quite strongly in the middle, which means that if we want a high purity of A, we would have to capture somewhere around here. And if you want a high purity of B, we have to capture somewhere around here, and we would lose most of our protein because here we still have this mixing. All right, so let's look a little bit how one can optimize such a process. We're going to look into fractionation. For this, we're not going to build the whole system again. We're going to load a pre-available model for a load, wash, elute system, and we're going to just execute this. So this is how the system that we're going to look at looks. We have 3 components, A, B, C, and a salt. And as you can see, due to the different absorption rates, they elute differently from our process. Next, we're going to add a fractionation. So this is that we are capturing the product at the end of our outlet, and let's say we want to capture molecule A, we can define a manual capture. So we say after 15 to 25 minutes is what we want to capture, which would be all of this. And this is obviously targeting product A. And this system can now give us some performance values concerning these this fractionation that we did. So we can see here the purity. With these fractionations chosen, you would achieve a purity of A in this fraction of around 86%. Obviously, because we have some of B overlapping in here. And we would recover around 96.5% of all of A, obviously because we are losing this amount of A down here. We also have some parameters for the productivity, the buffer consumption, and other parameters that might be interesting. However, for us now, interesting is recovery and so yield and purity. So next, those were manually chosen points at which we would fractionate, but now we want to optimize this. And now we can use the functions available in CADET. And by setting it up like this, we tell the system, okay, please give us the fractionation time so that we achieve a 95% purity in our fractionation for C in this case, right? Not A, but C. And here we can see the system tells that, okay, if you want to achieve 95% purity for your component C, you have to stop your fractionation at this time point because obviously now B is bleeding into it. So as you can see, the purity is 95%, and the yield. Where is the yield hiding? Well, the yield is hiding somewhere where I can't find it right now, but you could also get information about the yield. Let's maybe try A again, right? Before we had like 85%. 85% purity, and now we want to have 95% purity. And as we can see, this was the manually designed fractionation range, and this is the automatically by the system calculated fractionation range. And you can see we have to start collecting a little bit later to achieve our purity. Here the recovery, we now recover around 94.8%, and before we recovered 96.5%. So we are losing a little bit more of A to achieve a higher purity. Okay, and with this in mind, we can now look into how to optimize our elution process. So here we loaded the system at some point and we are now eluting, but we could make a change to the loading. So how much do we load? Or we could also make a change to how we do the gradient, maybe make it more flat, maybe make it increase the slope. But we can now use this model and try different parameter pairs to achieve better yields or better purities. And for this, we again loading this optimization problem, which is prefabricated by the designers. And now we are gonna add some variables that we want to optimize, right? So the cycle time, this is the time for the cycle time. This is the time for the elution gradient, and we also want to optimize the feed duration. So how long we are actually feeding before we start the elution. So these are two parameters that we want to automatically optimize. And we add some constraint on how the relationship of both of them is going to be, right? We don't want the feed duration time to be longer than the full cycle time because then there's no more elution time. We then load our simulation and we set up some target parameters. We want to achieve purities for both components in the system, A and B, of 95%. And here we have some ranking matrix. So this is how these results are evaluated. And then at the end, we're going to set up our optimizer. So we'll be using an automated optimizer, U_NSGA3. So this is going to run on 6 cores. We're going to have a population side. So this is a genetic algorithm. So this is going to do multiple runs of different populations in each generation, and then take the best result or take the best results from each generation, and from there start again with the optimization process. We have two parameters that we want to optimize in a range of around 10 minutes, 10 seconds to 600 seconds each. So we have two parameters, so we say 16 population size in each generation, and then run this for maximum 8 generations. This system will automatically stop if the improvement is not fast enough. Now we let this run. This can take some time because obviously in each generation this now has to run the full simulation 16 times. So we have to wait a little until we get the first results from our experiment. All right, so here we get the first result from the first generation. We tried 16 different combinations of these parameters, and we found out that the best parameter pair would be like a total process time of 350 seconds. And of these 350 seconds, 67 seconds should be used for loading our system. And the target evaluated function has a minimum of 0.02.6, and this is what the system is optimizing for. However, it says that this is not satisfying the linear constraints. In our simulation 2 or the second generation, we see that the same results returned, and in the third generation, we can see that the variables are a little bit different, but the evaluation at the end is much higher, right? So this is higher than our solution before, which was 0.02. And now in the fourth generation, we can see the change is much, much smaller. Here we are getting to an even better process. So the system is now working step through step through step, trying to optimize our process. All right, so in the fifth and the sixth generation, there were no better results found. It will probably stop after the eighth generation because no better process was found. And then at the end, we will probably see that these are the best available points right here. So we should run this process with 166 seconds of total cycle time and 61 seconds of load time. All right, this was a quick introduction into what is possible with chromatic field or mechanistic modeling of chromatic field processes using the software CADET. CADET is, I would say, the rising available software used for this type of modeling because it's open source and free to use. It does have drawbacks compared to other available systems. One being that you don't have a nice interface, right? You are working on this pretty core modeling programming basis. So you have to invest some time to understand these systems a lot. However, they give you a wide range of flexible options in how you want to design your systems, and you can do almost any process with these. And as I said, it's open source, free open source tool, so it's really strong, has a really strong positive impact as that. So if you're interested to learn more about CADET and how it works, please feel free to join the seminar, the practicum at the end of the semester. You also get ECTS for this, so you also get credits for this semester. It's a one week seminar where you work yourself. You yourself work a lot on exercises, and there's a handout at the end. So if you're interested, feel free to participate. And thank you very much for attending this lecture.